right. It's time to start. So today we are going to continue our discussion from last time about message passing and junction tree. In the last class, we discussed the message passing in very intuitive sense, and also mentioned the idea of the junction tree and merging a set of the random variables into a cluster and sending the messages basically between clusters. So in this class, we are going to discuss it in a more formal way, basically to do what we had as an intuition to make it more mechanical, so that like if you are given a graphical model, you can go and implement it. So a little bit of review from last time. So if you remember, we had a graph last time, and we basically converted the directed graph to undirected graph, moralized it, and we had an ordering. So here I'm showing the factorization of the probabilistic distribution of this random variable. So to give you an idea, so let's say that this is the joint distribution of the life of the graduate student. So if he wants to do good in an exam, he must be intelligent, but it also depends on the difficulty of the grade and also coherence of the exam. And then if he gets a good grade, get a good letter, and gets a job and become happy. Anyway, so then we had an ordering for elimination of the random variables. Like I showed you similar graph last time. And based on the ordering, we start removing the random variables and introduce extra edges between the variables that are not connected, but the connection are introduced because of the removal of the random variables. So that was basically the variable elimination in a nutshell, so I'm going to make it formal. And during the process of removing, every time that we remove one random variable, like there was one click that was involved in the process. So when we were removing C, it was a click, it was the factor between C and D. And then when we are removing D, basically we are removing this random variable, there is a click of random variables D, I, and G. And so on and so forth. So we also talked about this idea of a message passing. We gave an example that, well, let's say that we want to count the soldiers, and all of them want to know how many soldiers are in their squad. And we basically view it as a message passing that the soldier receives a message from its neighbor soldiers, and it combines its brief to it and send the message back. And when all of the messages are arriving at that soldiers, he combines all of this information and knows how many soldiers are in the group. That was basically the discussion that we had last time. We also mentioned that so basically the belief was combination of all of the messages that this guy received from its neighbors. We also mentioned that, well, that works for a simply connected tree, but as soon as you have a loop in a graph, you are in trouble because we have this problem of asynchronicity of the graph, of the messages, and then we have to stop and all of that. So we are going to handle that partially today and later on in approximate information inference. We also mentioned that, well, the remedy to this problem of loopy graph was to, instead of passing the messages between the elements, let's pass the message between cluster of the nodes, that this cluster of the nodes are introduced during the variable elimination. That as a result, instead of, so we can convert a graph with a loop, with a cluster tree that each of the nodes in that tree are set of the elements, and the message are passed between clusters. And then we have no problem in that sense that, like, well, right now we can do the message passing in this click tree, and but we also mentioned that, well, because the problem in general is NP-hard, there is something that we are hiding here, that if we do, for example, if you choose the variable elimination in the wrong way, we will end up with bigger and bigger clicks, and the size of inference, the size of the summation is exponential with respect to the size of each of these clicks. So overall, there is no free lunch. But as I said last time, we only gave you the general idea. We're going to make it formal basically today. So what is this message passing? So we first going to discuss the idea of a message passing and singly connected graph, and tell you all of the details of the implementation and when it can be useful and when it's not, and then we'll extend it to the cluster, to the junction tree. All right, so a little bit of reminder. I hope you guys remember the factor graph. If you remember that it was a bipartite graph, that one side was random variable and the other side was factors. And so circles represent the random variables, square represents factors. So all of the connections are between a set of random variables and a factor, so the nodes are not connected to each other. And edge represent that, for example, if this is the factor, the node represents all of the random variables that are inside of that factor. So hopefully you remember that from the third class. We also mentioned that it's sort of like a unifying approach of connecting directed or undirected graph to this way. This is not a way to read things like an IMAP prompt, but it's a way that you can represent factor representation regardless of you have directed graph or undirected graph. So it's very useful for the sake of inference that we are going to discuss today. All right, so again, so it is a general way of representing undirected graph and undirected graph, and so it's introduced by Perl in 1988. So we are going to talk about belief propagation or message passing in acyclic graph, and then later on say that how this notion can be extended. All right, so let me give you a little bit of notation that hopefully you already know, but because we are going to be using this notation in an entire talk today, let me introduce that first. So let's say that I'm given a factor graph. It's coming from either directed or undirected graph model. So I'm going to use, whenever I have something like a curly variable, I'm talking about sets. When I have the normal letters, then we talk about random variables. So this is square represent a factor. So here, for example, I'm representing the factor tree that are basically is as a result of conversion of some high order HMM for problem speech tagging. So this is just an example. So I'm using alpha, beta, gamma, things like that to represent a subset of this node. So here, so if I have n random variables, so this alpha represents a subset of these elements. And remember that the Gibbs distribution was multiplication of all of these factors plus some normalization. So here I'm representing that as bunch of factors. So this is a function, and this is a set of random variables that are enumerated by alpha, and they're multiplied all together and produce C. To produce Px normalized by C. What are these factors? For sake of this talk, let's say that we are only talking about discrete random variables. It can be extended later on for continuous, but let's be coherent. And so each factors, you can view it as so all of this information about, so here is a unary factors. Basically, a factor is connected to only one random variables. And if this random variable is discrete, we can view it as a vector, right? And and for the binary factors, for example, this guy, that is basically a function of two random variables, you can view it as a table. So and so on and so forth. So for example, if we are talking about a factor that's as a function of three random variables, you can view it as a tensor of order 3, right? Hopefully, we have already discussed this, but I need to make sure that we are all on the same page. All right, so let's start with an example. So let's say that we are given this factor graph, and it's coming, let's say, from a directed graph model. So the factorization on the top is a joint distribution of P, A, B, C, D, and E. All right. So it's obvious that like this can be converted to this factor graph. So basically, this is the term that involves A and B. This is the term that involves A and B and C. This term only involves C, and so on and so forth. So it's basically the same factor representation. It's like same joint probability distribution, only represented in the form of factors. Okay? So now let's say we are interested to compute the marginals of PA and B. So that means that we have to integrate out or sum over the rest of the random variables. So we have this representation, or let's say that right now we are talking about only a factor graph. So we have this representation. It's basically here F1, here is FA and B. We are talking about it as a PA given B, but it doesn't matter. It doesn't have to be normalized or anything. So let's focus on the general factor tree. And now we have to sum over C, D, and E. We discussed last time that, well, there's a naive way of doing this, which you have to enumerate all of these states. That's a bad idea. Smarter way to push this, to combine this term and push this sum forward and focus only on a subset. So here, if I had the sum outside, I'm pushing, for example, sum over D and focus only on a term that has only D. And these are the term that has term C and D. Okay, so far, this is the things that we discussed last time. Now, we are going to give you, so I'm going to give you different interpretation of this. So let's think of, so if you remember, when you are summing over D, summing over E, this is going to be a new function of only what? What is remaining, right? D. So we are going to interpret this as a message that passes from factor F4 to D. So why? Because there is something, the factor F4 is involved, and we are getting rid of all of the things that are on the right side of this. And we are viewing this as a message that sends from a factor to the node. And similarly, so for this message that is F5, we are going to interpret this as a message that goes from factor 5 to the D. Right? So let's go on with this interpretation and see if you guys can recognize what the other message would be. So this is the message that goes. This is the message that goes from factor F4 to D, and this is the message that goes from factor F5 to D. So what would be this term? If I want to go with this interpretation, what would that be? Can you write it as a message from either factor to a node or node to factor? It has only C in it, right? So C should be receiving it. And there is one factor involved, which is 3. So it should be a message from this guy to this guy, right? Okay. What about this? What about this term? I mean, I've already written that, but. So we basically view this as a. So we basically view this as a set of messages that either goes from factors to the nodes or nodes to the factors. So if you look at the patterns of the messages that are sent between factors and the trees, you see this, that every time that there's a message that goes from a factor to the node, there is a function of the factors involved in it. And when there is a message that goes from node to a factor, it's only multiplication involved. So this is basically the procedure that we follow from the rest of in the rest of the lecture to come up with an algorithm for passing these messages. We converted our original graph, which was either directed or undirected, to a factor tree. And now we want to send messages in this bipartite graph. Remember, this factor tree is a bipartite. Either the message goes from factor to the node or node to the factor. There is no message between nodes because they're not connected, right? So now we have to come up with the message that, well, if I'm a node, I want to send a message to a factor, what should I send? All of the information is already in the factors. I don't know anything, right? So, and the factors, if my factors want to send a message to a node, so it has a function to apply, and also it receives message from the others. So the way that we are going to do that is as this. So let's go back to the same examples that I gave at the beginning, that we want to label. So we are given a sentence, and we want to label each of these words in a sentence as verb, adverb, determinant, and things like that. So we can view each of these words as a random variables and the dependencies between them as a factor. So let's say that I want to, So each of these, x, y, and z, so here I'm showing only part of this graph column, that each of the circles represent one random variable, so let's say a word. Factors combine information from the rest of the board. So you can view this as for example, the message, intuitively, a message from a random variable to factor would be, my other factors thinks I'm a node. But this node, which here represents one word in the sentence, has only received information from the words behind it. So for example, let's say that if I write table, so let's say that this is the word. So far it has only received message from this side, but it has to combine information from the other side to consolidate what the label of this verb should be. So the factor, so here, each of these are one circles represent one random variables, and the factors between them basically denotes the connection between them. So how does that work? So it's basically both of these messages that come from left and right judge a label of that random variables. One side says that based on the information that I've collected so far from the left, this must be my label. And whenever I receive the messages from the right side, it says that based on the information that I received from the right, my label should be something else. And at the end, when it receives all of the messages from right and left, it combines them together in a form of multiplication and forms a belief. And that's basically the general idea. And this general, yes?
Do we ever repeat this process again? Is there a benefit to that? For example, like cat at the beginning, we don't know if it's a name or an animal. So we send all the information down, information gets sent back, and then cat can update.
Exactly. So if you have, so I'll talk about the scheduling in terms of message passing, but if you have a singly connected graph, which means there is no loop in it, you start sending basically messages from a root to all of the leaves, because it is a tree, you can pick one of them as a root, doesn't matter. Send all of the messages to leaf, and whenever leaf receive all of the messages, send the message back. So you send the message down so that everybody receives the message, and then send the message back. So you don't need to do it more than this. Because send a message and receive a message, there's no extra message after that.
But the earlier nodes can't somehow update their information and pass, cat, for example, could say, when it gets information passed back to it, it could say update its belief about what it is itself.
So
and they can repass that information.
So basically your belief is updated whenever you have received all of the incoming messages. So for example, in this case, you have received all of the incoming messages from this side, but you haven't received all of the incoming messages from the other side yet. And to receive that, you have to wait till the message goes all the way to the end. So basically you update your belief when all of the incoming messages have arrived. But you can only, so at the beginning, let's say that this is the somewhere close to root, right? So root just sent a message to this guy. So it says that, okay, I received 2 of the message, but there is still 1 remaining, right? To receive that message, the other guy has to receive all of the messages back to his children and children and children until it reaches to the bottom. And then they start sending message back. So there is, after you receive all of the messages, there is no reason to update because it's a fixed point. So the form of the message is basically a vector. So the vector of it, for in this case, we are talking about the discrete case, is basically the form of the vector of the numbers that for each of the state represent a number. So here, if this node has 3 states, verb, noun, and adverb, the form of the message is a vector of 3 numbers. And so overall, in a message passing, we have basically variables and factors, and we have a message that goes from factors to the nodes, nodes to the factors, and we also have a belief for each node and for each factor. So you can view it as a table. We have either variable, which is a circle, or we have a factor, which is a square. Each of them have a belief, and each of them send a message. So the belief is basically multiplication of all of the incoming messages. It doesn't matter you are random variables or the factors. Whenever you receive all of the incoming messages, you form a belief. For the messages, there is a difference between the way that node works and the way that factor works. So whenever, for example, node x1 wants to receive send a message to another factor, which is, for example, side 3, it has to receive all of the rest of the variables and multiply them. And similarly for the factors. So what are the forms of these messages? So let's talk about the belief first. So as I said, for the variables, whenever it receives all of the random variables, all of the messages from the rest of the factors it's connected to, is going to multiply them all together. That's the way that the belief of the node works. So in a term of discrete random variables, so let's say that x1 has 3 states, verb, noun, or something else as a 3 state. And so these 3 states get multiplied to each other. It's like the 3 vectors that get Hadamard product with each other, like element-wise product. And forms basically a belief. So here, for example, the belief for V1 is going to be multiplication of 0, 1, 1, and 4, which is going to be 0.4. Similarly for factor, so how the message is passed. So the way that message passed depends on whom you are sending message to. For example, if variable x1 wants to send a message to x3, it has to combine all of the information from them and accept the message that he got from this guy and send a message back to it. So that's how this algorithm works. So, and similarly for factors, the factor belief is basically slightly different than the node belief, because for the node you receive all of the messages and there is nothing done in the node level, but the factor has a function to apply on all of the messages. So here in this case, let's say that we have a factors between x1 and x3. So it receives messages from x1 and receives messages from x3. So each of the messages from x1 and x3 comes in the form of a vector. Now, factor has a function to apply it on. So the way it works is that, let's say that I have two random variables. They don't have to have the same cardinality. So for example, let's say that in x1 has 3 states and x3 has 2 states. So the joint function of between x1 and x2 is a matrix of 3 by 2. So the belief of this basically factors is multiplication of all of the incoming messages multiplied by the factor that it has inside of it. So the way it works is that you can view it as basically an outer product between messages and element-wise products with the factors. So another way of writing this is that if I call this x and call this y, I can multiply x outer product y, and if I call this f, this would be the function that's applied. So this forms a belief of the factor. Now, how does the message goes from a factor? Yes?
The previous slide, the output table doesn't seem like an outer product. The yellow one does, but I don't know what the red one is.
So the red one is the factor, right? It's the same thing that I showed in the previous message, just rotated.
Yeah. Okay, I see.
Right. I just rotated it to make sure that. So one of the sides are 3 by 1, and the other side is 2 by 1. So I'm just showing that the directionality that it multiplies. Another way of writing it is the same way I told you, in the matrix format. Clear now? Okay. So now let's say that factors wants to send a message from to one of the random variables. The way it works is that it gets all of the random variables around it, it multiplies with the factors, and integrate out the rest of the random variables that are not in the same set. So let me give you an example. So let's say that this factor is receiving message from x3. So it's going to multiply the message from x3 with its own factors, the influence of that factor, and integrate. So because it's going to send the message to x3, let's say that x3 has 3 random variables, v, p, and n is 3, right? So if this is the message that's coming from, this is cardinality of 2. The message coming from the x3 is cardinality of 3. This should be 3 by 2. But x1 only understands the message in the language that it has. So it's like, if you have any other things, you have to get rid of them. You have to integrate them out. So the way it works is that it receives all of the messages from surrounding nodes, multiplied all of them except the one that it is sending message to, applies its own factor, and integrate out all of the variables except the one it's sending the message to. So here in this case, it's going to be it's receiving only one message. So here is going to be only the message that comes from x3 to the factor psi 1, and it's going to apply. So this is going to be a message that's coming from that guy, and then it's going to apply the factors psi 1 on it. So remember, psi 1 accepts 3 random variables, x3 and x1. Because it's going to send the message to x1, it has to sum over all of the random variables that it does not understand, that in this case is going to be x3. So is the setup clear? So the way it works is that it's going to multiply the message that's received from x3 with its own factors, sum over, because it's going to send a message to x3, and x3 has only 3 states. So it's going to sum over these two states and send a message to x3. So in summary, this is how the different messages. So remember, we had 2 kinds of message. Message that goes from factor to the node and node to the factors. So if a variable or a random variable send a message to a node, what it does is that is gonna multiply them all together. So, for example, if this node is gonna send a message to these factors, all it does, the event that happens at this node is that it's gonna multiply all of these messages that's received from the rest of them. That's it. That's a procedure. Similarly, for the factors, when it wants to send a message from this, so let's say that we want to send a message from this factor to this node, what it does is that it's going to multiply all of the messages received from the other one, applies in its own factors, get rid of all of these random variables, and send it to this one. So let's try an example. So x1, x2, x3. So this is like I'm showing you part of the graph. So let's say that's psi 1. So first of all, tell me what should be the form of psi 1. What are the arguments of psi 1? Huh?
x1, x2, x3.
Yes. So because it's function of 3, x1, x2, and x3. So now let's say that these factors wants to send a message to this guy. What should I do? So let's call this one mu1, mu2, and we want to compute the message that goes from psi 1 to x3. What should I do? Okay, multiply mu1 and mu2, which by the way results into what? Matrix, right? Because it's autoproduct. Yes, it's autoproduct. And then what?
Then you multiply by psi 1.
Yeah, multiplied by psi 1, which here is the tensor, right? Right.
Yeah, because it's a 3.
And then what?
Marginalize over x1 and x2.
Marginalize over x1 and x2. So you are sending message to x3, you have to get rid of all of the rest. Right? So now, let's say that x3 wants to send a message to psi 1. What should I do? x3 wants to send a message to psi 1.
Does it just send mu4?
Exactly. Right. So you want to send a message, all of the incoming messages you multiply, this guy is only receiving 1. So just send that.
What
Yes.
could you explain why U1 and U2 are orthogonal?
Orthogonal?
Yeah, you said they're orthogonal,
Yes, orthogonal. Mu1 and mu2 are orthogonal. I don't think that is it.
right? So are they a matrix again? They are both of the same dimensions, right?
So mu1 and mu2, no. So it's basically, okay. So mu1, so what is the dimensionality of the mu1?
I didn't get that part.
Okay, so the dimensionality of mu1 is coming from x1, right? So it would be as many states that you have in x1. So it's going to be cardinality of x1. So mu2 is coming from x2, right? So it's going to be the cardinality of x2. So they don't have to be the same. So one of them can be, I don't know, 2, the other one can be 10. But you're doing autoproduct.
Oh, you're doing the ortho product?
Yes, so it's going to be 2 by 10. So mu1. And at the end, when you want to compute the marginal, you wait until you receive all of the messages. So you send all of the messages from the root to node, and node to root, and you multiply them all together, and you have your marginals. So if I want to write it as an algorithm, yes.
Could you go back to the previous one?
Yes.
So the equation there also has a max. Where is that max?
Max?
Yeah, in the factor to variable message, there's a max.
Oops.
Over the,
It shouldn't be max, it should be sum. I'm sorry for that. I'm sorry. So later on, we're going to talk about max. So my apologies. It shouldn't be max. It should be
is that
sum.
like a greedy approximation?
No, it's not really happening. Actually, I'm going to talk about max in a few slides down the road, but I guess like when I was making it, I made a mistake, so it should be sub. It shouldn't be max. We will see the max one later on. So far we are talking about only exact inference. There is no approximation. So if I write it as an algorithm, so we start with, we basically initialize all of the message that goes from the nodes to factors to node as 1, and follow the procedure. So we first said, are you a factor or a node? You are sending a message to a node or factors, right? And then we follow one of these procedures. If you are a node sending a message to factor, you just multiply all of the incoming messages and send it. If you're a factor, you multiply all of the incoming messages, apply your factor, your operation, sum over the rest of the values you have received, and send it. That's the operation. Now, so the way it works is that we are talking about a cyclic graph. So what you do is that you choose one of them as a root. You send all of the messages down till it receives all of the leads receive it. So now all of the leads start sending a message back. So you start from the root, go all the way to the bottom. Root send a message back, and root receive the final message. The algorithm is complete. The setup clear? Yes.
Why setting it to 1?
Huh?
Why setting them to 1?
You have to initialize with something. If you initialize, so you at the beginning, you don't have any belief, right? Say that the multiplication 1 doesn't do anything, right? 1 multiplied by anything, that number, right? So I have to have a good rule to do nothing. It's a rule to do nothing. Okay. Now, so going back to the summary table, so the belief of each node is multiplication of all of the messages arrived to that node, and belief of the factor is multiplication of the messages to that factors, multiplied by its factors. So if I'm a node, the belief of me as a node is multiplication of all of the messages that I've received. If I'm a factor, is multiplication of all the messages and belief in addition to the factors that I applied on. And if I normalize this, I get the marginal distribution for free. So basically, you send a message all the way to root to node and back, and you get the marginals of each node and factors for free. Now, for the messages that goes from variable to node, as I mentioned, if you're sending a message to a factors, you receive all of the messages from the rest of the factors and multiply all of them and send it, and similarly for the factors. So it's basically the same thing that I told you. So for a general acyclic graph, you choose one of the nodes as a root, doesn't matter which one. You start sending messages, for example, from the roots back up to the leaf. And whenever you want to, basically the idea here is that if you want to send a message up, you have to wait until all of your messages are there. So if you want to, for example, send a message from side 1, to X7, you have to wait till all of the messages are there, and then send it. And similarly, on the way back, when the root receives all of the messages, it starts sending the message back. So to send the message back to, the same rule applies. If you want to send a message from a factor to a node, you have to wait until all of the incoming messages are. So if the scheduling of the message passing clear? Okay. Now, there is so you probably have observed that to send a message, I still have Maxter. So to send a message, basically, if I'm a node, I'm sending a message to a factors, I have to multiply a bunch of messages to each other. And if all of these numbers are less than 1, if I multiply a bunch of values less than 1, at some point, I'm going to run into precision problem. Because if you multiply a bunch of float number, I mean, you have either double or float as a way to store these random variables, these messages, and you run into precision problem. So a remedy to that problem is basically operate on the log scale instead of on a multiplication scale. So instead of sending the messages, the message, you send a log of the message. So then your multiplication becomes summation. So basically, sum of the messages become multiplication of the log of the messages, and you get the log of the message. And oh, here I have summation. So, but what should we do whenever we have a summation? So do people see that why multiplication is like is sort of like a remedy to just multiply them? Like why operating on a log scale is better than operating on the actual values? Is that clear? Okay. Now what should I do for that? Because here this part is fine. These can be like this summation, this multiplication can become sum on a log scale, right? Here I'm using lambda to show the sum, the log of the random variable. So this is fine. And then I'm multiplying a factor. This is still fine because these can become still a sum. But then I have to sum over something. What should I do there? Yes.
You can use you take the largest exponential out,
Right.
and then the rest will be smaller numbers, and you can basically deal with them.
Okay. Can you explain? That's the correct answer. But like, can you explain why that helps? So let's say that I have, I don't know, like my messages is going to be e to the lambda 1, e to the lambda 2, and so let's say I want to sum over all of this. How does that help?
That basically reduces the largest order that you have among the summons, and therefore increases the precision in a way.
So basically you find the largest one, and you say that I'm going to say lambda 1. So this is going to be 1. This is going to be e lambda 2 minus lambda 1. And this is going to be e lambda 3 minus lambda 1.
Yeah, all of those are smaller than 1. So.
Right. So it's basically that basically a way to get rid of this precision problem. When you want to sum over over a bunch of messages, find the biggest one, factor it out. So if you factor it out, when you apply the log, it's become just a number add to the rest of it. So you don't run into precision problem. So this is a note on implementation of the message passing, that in reality, nobody does the message passing in the actual scale. Everybody implemented in the log scale. And these are the tricks that you can use during the implementation. Hopefully you will see that in the homework. So, all right, so we talked, one of the things that we discussed is that, well, we only I've talked about message passing to compute the marginals. What if I want to compute the maximum MPA, maximum assignment probability? So the same tricks apply. So let's say that we go back to the same graph. So let's say we have a graph of 3 factors. So that has, these are basically 3 factors, and I want to find the maximum assignment of these 4 random variables. What should I do here? Remember, you push the sum forward. So what should I do for the max? Can I do max over each of the random variables separately? Can I or cannot? How many people think I can? Okay, so how many people think I cannot? Okay, so what about okay, so all right, so what is the most, if I do it naively, I have 4 random variables, let's say each of them have 2 states. So I can make a table, it's going to be 2 to the power of 4 and then search for it. That's the silly way of doing it, but it's going to be expensive. But if I, stare long enough to my factorization, I see that, well, x1 and x2 are dependent. x2 and 3 are dependent in one function. I can't do anything with that. But it seems that x4 is only dependent on one factor. So I'm going to push my max all the way forward. So I can get rid of 4 here because it's just one factor, right? And view it as a message. So the resulting is going to be a function of x3. So I can basically view it as the same thing, as a message passing that comes as in the form of x3. So this is going to be a message from x3 back. And then I have this term that's only function of x3, right? Because I got rid of x4. And continue. So it's like a dynamic programming. So you first identify one element that is like single and alone, you get rid of it, and you start peeling off your problem. So that basically the same idea applied when you want to compute the maximum. So you can view this as a message passing, except that instead of sum, you have a max. So so the rules basically is exactly the same. When a node receives, the nodes are receiving messages from factors, you just multiply it. It's exactly the same rule. But when a node receives, a factor receives the message from the node, instead of summing over the rest of the variables, it's going to max over this. So here the max actually has to be there. And at the end, when you want to say that what's the marginal probability, what's the marginal assignment of one random variable, you receive all of the messages and you find the maximum. So it's basically exactly the same program, the same procedure, except that the sum is replaced by max. And the same trick applies. Is that part clear? Because if you don't answer, I feel that everything's clear, I just move on because we have a lot to cover. But if you tell me it's not clear, I can clarify it now. Because you'll see that in the homework. Yes?
When would you use one over the other?
It depends what you want to compute. Okay. So let's say that if you ask me that I have a singly connected graph and I want to compute the marginal of px equal to 1. So I have this graph. So my factorization is what? So it's my psi1, x1, x2, psi2, x1, oh, sorry. Right? This is my factorization. So if you ask me, give me the marginal of x2, what is the marginal of x2? Then I have to do message passing with sum. But if you ask me, what is the max of px1 over x1? So they're answering two different questions. One of them is marginalizing out. The other one is finding the maximum assignment. So these are for two different queries. Now let's make it a little bit more complicated. So let's say that I have this graph of x1, x2, x3, x4, x5. psi1, psi2, psi3, psi4, psi4, psi5. Okay? This is a tree, right? Okay, now let's say I ask you, give me the maximum assignment of x3 and x1. What is this? What should I do for this? From the factorization, I can write joint distribution, right? I can write the joint distribution of px1, x2, x3, and x4, and x5, right? I can write this from the factor tree. It's basically multiply the factors, you're good, right? Now, what I want is that I want to maximize over a subset of this, right? So what should I do? So first, I have to compute this and then do maximization, right? So let me make it slightly easier. Let's say that I'm not interested in px1, x3. Let's say I'm interested in px1 multiplied by x3, right? I come up with a function. I say like x1, marginal of x1 multiplied by marginal of x3. And this is a function of x1 and x3, right? I want to compute it. So first, I should be able to compute this and this, and then maximize. What method? So what operation I should do to get the x1? What kind of message passing I should do?
Summing.
The summing, right? Because you want to compute the marginals, you first have to do the summing marginal to get rid of all of them. So it's basically to get the px1, you have to sum over all of the random variables that are that are irrelevant. So x3 and x4 and x5 of this guy, and then you get a px1, and similarly for px3, and then do maximization. Yes.
So I'm a little confused about belief versus
Message.
message. Is belief something that you can only get at the end of this process?
Yes.
And then, so does that mean that you would do one run through this algorithm and you could answer multiple questions at the end? So that you
Yeah.
Okay,
Exactly.
so then it would just require you to do normalization of these beliefs to get the marginals?
Exactly.
What about if I wanted to do the maximum assignment? I would have to redo I'd have to do it with the maxes.
Yeah. Exactly.
And I could no longer answer the questions about getting the marginals, or do I still get that?
So if you are interested in a query that involves maximization, you have to send the different messages. But the good things about message passing is that so let's say that you send all of the sum messages, sum product messages, right? You send and you store all of the messages. And then you can compute all of the marginals. You can compute px1, you can compute px2, because you multiply all of the incoming messages, normalize. That's all. So some of the marginals that are explicitly represented in a factor tree can be basically computed for free by multiplying the messages. But that's not all of the marginals. So for example, if I come up with two random variables in the arbitrary location on a tree, then computing that would be slightly more challenging.
We haven't discussed that yet.
We haven't discussed it, and we won't go over that. So this is basically gives you a marginal of each of the nodes.
So the answers we're able to answer based on this are if there is a factor that exists that has the same form.
Yes, you can get it. Exactly. So if you have a factor that has random variable x1 and x2 and x3, it gives you the marginal of x1, 2, 3 for free. So what about the connected tree? So let's see what kind of problem happens when you have a loopy graph. So let's say that this is in this graph ABC and there's a loop, and I want to compute. So the joint probability distribution of ABCD is this multiplication of the factors. Now, if I want to marginalize D out, I can push the D inside, right? I can push the summation over D inside and sum over these two terms. The resulting terms is going to be a function of A and C, while in this graph, there is no connection between A and C. So either you have to adjust the structure of the graph every time you send a message, which is basically you're doing click-tree under the hood, or if you have a loopy graph, the vanilla version of the message passing won't work. So basically, if I want to do this, After I push the message forward and get rid of D, I have to connect A and C immediately. So basically, in the following, algorithm junction tree is a remedy to this problem. That for many of the graphs that we have a loop in it. Even if you have a DAG, after we remove the arrows and moralize the graph, we end up with a loopy graph. So how can we do message passing? So before that, we have to introduce a notion of a quick graph. So the quick graph is basically a way to represent a function. Yes.
Could you go to the previous slide?
Huh?
Could you go to the previous slide?
Yes, sure.
The reasoning that you used sort of confused when you don't have like one of the edges there too. If you start from D,
Yeah.
you still have that problem, don't you?
Doesn't matter. You have a loop. It doesn't
No, I'm
matter
saying
which
that-
one I start.
No, I know. I'm saying that take one of the edges out, so it wouldn't be a loop anymore.
No, but if I push it, so you should, this graph is just to represent the factorization, right? I push the summation over D inside, and I have a term that D's factor out, but it involves C and A. So let's say that if I got rid of this, so you only have a factor that involves C and B, and a term that involves A and B. What happened to the one that's with A and B, A and C? You have it here, right? So so when you are doing forget about the graph for a second, right? All I want to do is a summation, right? I push the summation term inside, get rid of D. I end up with a term that has both A and C in it in a joint term. If I naively remove the term D and disconnect it, there is no joint term between A and C. While in my summation, there is a joint. So my factor tree does not represent the reality.
Okay, I'll ask this later.
So the quick tree is basically a way to represent a function that comes in a form that in the following form. So let's say that you have a set of functions that defined on a subset of random variables. So each of these curly psi 1 to psi j's, x1 to xj's are basically a subset of the nodes. And click tree is representing the functions that are multiplication of all of the factors divided by the subset that are intersection between nodes. So for example, if I have, let's say I have very simple case. So in very simple case, x1 is a subset of bunch of nodes, and this is subset of bunch of nodes too. So let's say this is A, B, C, and this is B, C, D, right? The intersection between these sets are basically B is shared and C is shared. So quick tree is a representation. It's like you can view it as a data structure that says that I'm going to represent all of the function that comes in the form of any factors of A, B, and C multiplied by another factor B, C, and D. But then because they are shared, I'm going to divide it by another term that has the shared term inside of it. This is just to represent a function. So do not confuse it with the factor tree. But we are going to use it later on to see how it works. So to give you an idea how it is related to probability, let's say that I have this representation. This is the graph that I have. I mean, obviously it has a loop in it. So what is the form of the factor graph, right? So this is one click, and this is another click, right? Each of these click. This is the form of my joint probability distribution. You have two clicks multiplied by each other. So it can be shown, it's not actually hard to show, that another way of representing the same graph is to say that I can come up with, I can represent P, A, B, C, D as a function That's multiplication of A, B, C, and B, C, and D multiplied by something else that has the joint term between them, which is going to be B and C. This can be shown. So how can we show that? So basically, the clique tree of this can be represented this way. So, well, let's say that if I want to represent P, A, B, and C, I have to sum over the term D, right, for the joint distribution. So the joint distribution comes as ABC, BCD divided by Z, right? So I'm going to use Z here, right? And similarly for the other term. So if I want to compute P, B, C, and D, I have to sum over term A. C, B, and D. Right? It's clear so far? I just like, right? This by definition is correct. Right? Now, what I have to do if I multiply these two sides by each other, what do I get? I get two sums of A and D over this A, B, C. It's basically P squared. If I shuffle them around, I'm going to get this term. So because so remember, I'm taking A and D out. So at the end, I'm going to get P, A, B, C, D on one side, and the rest on the other side. So because of this factorization, I can represent this instead of factor graph as basically a bunch of probabilities adjusted by the term that are shared across them. So the general idea of the junction tree is as follows. The general idea is that it's a new way of representing graph in which the variables in a class are clustered together. So instead of representing, so it's like each of the nodes in the junction tree are a cluster of the nodes. And you're going to represent the joint probability distribution as the multiplication of the probability over each of the clusters divided by the term that are shared. And it's basically the inside is basically the example that I gave you earlier. We have to remember that because for the general tree, inference is NP hard, there is no free lunch. So we are hiding something, which is basically the same insight that I gave you last time, that although we are converting our loopy graph to a tree structure, we may end up with very gigantic cliques that inference over those are not polynomial. Nevertheless, we do that because sometimes we have an insight that we can come up with for some of the families of the graph, that cost either is affordable or it helps us in our approximation procedure. So let's go back to the examples that we had last time. So this is the same graph that I showed you earlier that is basically the life of a student being happy, so he has to get a good recommendation letter, he should find a job and be happy, and depends on the exam, and the grades depends on the difficulty and all that. So this is the probabilistic, is the DAG that we start with. So let's get rid of all of the arrows and get the undirected graph. The first step that we have to do is moralization. So if I want to moralize that graph, whom should be connected to each other? Difficulty and intelligence, yes. Letter and SAT, yes. Anything else? Grade and job. Right. So basically you are marrying all of the parents of the V structures. Right? We first moralize the graph, and we start our elimination procedure. So remember that finding the optimal elimination order is NP hard. But we come up with let's say that let's pick one procedure. So let's peel off from the coherence. So let's say I propose this ordering of the elimination. It's the same procedure I told you last time in the previous class. So we start removing C first. So that involves a click of C and D. So if I get rid of that, I don't need to introduce any extra node. And then we are going to eliminate D. So the factors that involves the term D in it is this triangle of the difficulty, intelligence, and the grade. So this is the second click. Because all of them are connected, I don't need to introduce any node. Next, I'm going to remove the intelligence. So if I remove the intelligence, the three terms that involve in this intelligence are intelligence, grade, and SAT. But if I remove the intelligence, should I add any node to this? Remember, C is already removed, D is already removed, and you are about to remove I.
Yeah.
Huh? Everything grade and SAT, right? Because you are getting rid of, so in a resulting tree, there is no I. So if I just naively remove it, there is no connection between these terms while they have I have a joint term. So I have to connect them to each other. So I keep going. If I remove H, do I need to connect anyone to anyone? Who thinks that I have to connect some nodes to each other? Who thinks I should not? Okay, why?
Because they're already connected.
They're already connected, right? And for the G, what about G? If I remove G, should I connect anyone to anyone? No, it's already full. Everybody's connected to everybody, so it's gigantic quick, by the way. It's 4 nodes in it, which is pretty bad. And the SNT, I guess, is quite clear. So what we did at the beginning, we started with the DAG, we removed the arrows, we moralized it, and we started with the elimination. We followed our elimination, and every time that a node needs to be connected, we just connect them. So basically, we end up with what is called moralized and triangularized graph. To be more specific, so basically triangulation, so you can view it in 2 ways. The triangulation is a procedure that whenever, for any loop in a graph that has a length of more than 4, there should be a coordinate. So what do I mean by coord? So it's like, if I have a graph which looks like this, right? So this one has a length of 5, right? This is the loop with a length of 5. The chord is basically a connection between non-adjacent nodes. So this one doesn't have a chord, but when I connect them with this, there is a chord. This is called chord. And this procedure is called triangulation, and the resulting graph is called chord. So there are 2 ways to do this. Either you start with moralized graph, you have an elimination, and you follow the procedure I told you, or you loop or search over all of the loops in the graph and make sure that there is a coordinate. You just introduce a chord. You get your triangulated graph.
So we just introduce it?
Huh?
You just add a chord just like that?
You just add a chord, yes. These 2 steps that I'm saying are equivalent. So to me, it's much more reasonable to view it as a variable elimination, because I know that if I remove that in my message passing, I'm going to introduce new terms that are connected, just connect them. But that's another way of saying exactly the same thing, sure. And so basically, so what we end up is basically a bunch of the trees. So you remember our ordering. So we first remove C, which has this click, this guy. And then we remove D, which has this click, which is D, I, and G. Right? And then we remove I, which was this guy. So I, G, and S. Right? And then we remove H, which was this, which is H, G, and J, and then we remove S, which is this guy, and then we continue. So these are our clusters. These are the clusters of the factors that are connected to each other. The first one involves C and D. The next one involves D, I, and G, and so on and so forth. So when I'm connecting them, so these connections is basically whenever there are two random variables, there are two clusters that they share some random variables, I just connect them. So C and D are connected to each other. So what should be the things inside? So what is the share across them? So it's like a D's shared, and that's it, right? So D, I, and G, and G, I, and S, there is a I and G share across them. So it's like basically I'm drawing. So although I don't have a space to draw it in the same ellipsoid rectangle that I had in earlier, it's basically I'm representing that for you. And if you follow this procedure, you have a click tree. I cheated a little bit here, though. Huh? No. So here, well, I've added more, but it's not. My cheating is not moralization. There should be some connection that's missing, right? There are some. So, for example, how about the connection between these two? What happened to that? They're sharing something. So remember, we had click graph and click tree. In click tree, the resulting structure has to be tree. So another way of thinking about it is this. You start with your elimination procedure, you come up with bunch of clicks, right? Bunch of clicks. Don't connect them. Do not connect them. So these are the set of the clusters that you get from variable elimination, right? And you start connecting them to each other and put an edge between them and then put a number on the edge that counts the number of the shares. So for example, so I can do C and D has only one variable share. D and I has two variables, so I'll call it 2. G, I, and S, and okay, so this is 1. And G, oh, this one is 2. G, yeah, wait, sorry. Okay, right? And J, S are 2. And this guy is 1. 2, right? And this one should be what? 2, right? And then connect the rest of them. So go over your elimination procedure, build your clicks, and you have a clusters, right? Connect the cluster, and the node between them is going to be how many variables are shared across them. So you won't end up with the graph. You end up with the tree. You end up with the graph, right? Now you want to have a tree at the size of the clicks. So first of all, it must be you have to go from a graph to a tree, and you want to make sure that the clusters are so that the clusters are the size of the clicks are minimal. So run a spanning tree on it, and you have your graph. This is another way of building the same thing. So basically, the procedure is as follows. Oops. Okay. Yes. So the procedure is as follows. Okay. So let me go over this. And then, so let's remember what we were doing in terms of message passing. So now, instead of sending the message before that, we had a message passing that was sending message between nodes and factors. So here, our variable elimination is basically getting rid of the random variables and summing over that and see what is connected. So you can view that as basically summation or a message that's passed. So here, when we're removing C and D, we'll get rid of C, right? So we can view it as this message, right? That C is removed and the message is sent here. In the next step, when we're removing this click and we're getting rid of D, we're summing over D. So the general idea is like this. Somehow you start from your DAG, or if it is under the graph, it's okay. So start with that, moralize it if it is needed. So if it's undirected graph, you don't need to do moralization. Triangulate it, have an ordering between them, ordering random variables to get the cluster tree. Build your tree structure and start sending a message. The procedure is the same as the message passing that I told you at the beginning of the class. So there are two basically routines. You first choose one of these clusters as a root and say that you invoke a function, let's call that function collect, right? So the collect says that I need all of the message from my children. I'm the root and I need all of the message from my children. So so here you have only one children here. You say that collect the message. So he said like, well, I don't have it. I have to call my message back. So it's like a recursive way of calling it. Until this message arrives at the children and said like, okay, I don't have any children. I'm going to send the message back to you. So you invoke this collect message. The first collect request received by the first children, and then the basically children at the bottom, and they start sending a message back. First message is back from the children, the leaves, and then arrives at the root. When the root receives the message, and say that now it's time to distribute, and distribute the message back. And it calls all of the children to distribute message back to their children, and so on and so forth. It's the same procedure. I just like write it as a program, as a recursive program. Except that here, instead of this notion of factors and the nodes, we have the clump of the random variables. And every time that you send a message, you have to send a message that, well, if this is the node A, sending a message node C, there is. So let's say this has a set of random variables. This one has a set of random variables, and there are a subset of those are shared. I'm gonna integrate out all of the random variables that this guy does not understand, and send a message. So formally, that's the way it works. So if I want to send a message from cluster B to cluster C, there is a set of random variables that are shared across them. I'm going to multiply all of the messages that I've received from the rest, apply my own factor on it, and integrate out all of the things that this guy does not understand. It's a very similar approach at the message passing that I told you. Is this part clear? So every node, every cluster of the nodes can be viewed as a big factor, right? So it receives all of the messages from the surrounding cluster, multiply with each other, apply its own function, and say that, okay, now whom should I send this message to? The guy C understands only a subset of my variables, so I'm going to get rid of the rest of them and send it. That's the procedure. So the formal algorithm is that you start with a graph, remove the arrows, or if it has arrows, moralize it, and then you have to do triangulation procedure that either you do it through variable elimination or do a spanning tree. Get the junction tree and assign the potential to each of these clusters and send the message. I know that it's confusing, but I believe that's the most confusing class of all time, because it's going to be the most important part of the course, because we have to do how to do it for the exact algorithm to understand how valuable it is to approximate it in the crazy graph. Anyway, so some facts about belief propagation. So belief propagation for the basically singly connected graph is exact, so there is no approximation. And so basically, you can run the vanilla version of the message passing in a loopy graph too, except that there is no guarantee that it converges. But there are theorems that even if you don't do the exact algorithm and say that, I feel lucky, I'm going to run my message passing, the vanilla version of my message passing on a loopy graph, most of the time it converges, although that there is no proof of convergence. There is alternative way of viewing the message passing as an optimization problem. that I did not cover, but you can view basically the message passing as solving a set of so-called fixed point operations. So it's like a fixed point operation looks like when I apply a function and basically gives me this. So if they say that I operate on x and get the x back, you can view the message passing as a bunch of operations like this. We won't go through that. So finally, I have to. So we had the zoo of the network that hopefully you're not confused with. We had a directed and undirected graph that are there to represent the probability, the family of probability distribution. These are the things that we say that this shows the independence. So please don't confuse this with the factor graph. The factor graph is we convert a UGM and DGM to show the factorization of the tree. It's not there for you to read things like IMAP or independence from. And finally, just to confuse you a little bit more, we have the directed graph and the undirected graph that every circle represents one random variables. We introduced ellipsoid that basically this ellipsoid is the cluster of the trees. But we needed this to do exact inference. So this basically concludes the exact inference of this course. I believe that right after this, the more exciting part of the PGM starts. But I have to tell you all the boring things, so you need to know that. Yeah, so that concludes the class. Yes.
So do you use p-graphs only when there's loops or?
Yeah. So basically, that's the whole point of doing this. Like when there is a loop, so you have two options. Huh? So let's say if there is a loop, you can see that I feel lucky and run my belief propagation on the vanilla version. There is no proof of convergence, right? That will give you approximate results. But if you only care about the exact result, you have to convert your loopy graph to a junction tree and do the exact message passing on it. So if you care about the exact, yes, you can do that. But again, there is no free lunch. You may not end up with polynomials. Any other question? If no, see you next week.